So in this video walkthrough, we're going to look at this neural net, this notebook that builds a neural net from scratch. The building block of any neural nets is neurons, and they're nothing more than a computation unit that does the uh, matrix multiplication, right? Essentially, um, for each of the neurons, we have a set of inputs, which are passed in form of vectors or tensors, and we also have the weights also in form of tensors, and we will have a bias so that we can model so that not all computation result in a pure linear relation, right? If we don't have the bias, then we just have a bunch of linear transformation between different layers. With the bias, we can introduce non-linearity. So that's what a neuron does. But to build a neural net, we need more than just a neuron, right? We have the activation functions, which again also add non-linearity into this. So here we have all the activation functions here and like what their range are and what they're best used for. So yeah, we basically code in um, the individual activation functions here um, as a derivative as a derived class of the activation functions, right? They each have a forward call and a derivative call. So those will be used in the forward pass and the back propagation. And then we look at the loss function. The loss function is really the difference between the computed outcome and the desired result, the difference between those. And this will be the objective function for us to minimize, right? We want to minimize loss so that our model is more closer to the true result, is more accurate. So yeah, the loss functions are the things that we try to minimize. So here it talks about the common loss functions, right? For regression, you have MSE, and for classification, binary classification, multi-class classification, you use cost entropy. Um, so yeah, we code the loss functions here. And then we have the layers, right? We talk about single neurons in the first section, and here's how we put them into play. We have a set of neurons serving as the hidden layer in between. And when we use matrix multiplication, uh, use batch processing uh, to get from the inputs to the outputs. Right. And when we hit the output, we would have we would be able to compute the loss, right? The loss function will compute the loss, and we want to minimize those. And how do we do that? We do that by backpropagation. So in the forward pass, we go from the inputs to through the hidden layer and to the final output, and we compute the loss. And then we use chain rules to compute the derivatives, or in the context of tensor or vectors, the gradients, the partial derivatives. So we want to descend or decrease the loss in the most efficient direction. So we find the steepest partial derivative, and that will be the most efficient direction to go. So we have the we get the new adjusted ways from the old one and just minus the difference, the partial derivatives. Uh, and this parameter is the learning rate, right? So this is how we learn or readjust the hidden layers, the weight from the result. And we do this through different iterations, and in the end, we should have uh, optimized the hidden layer with the weights being adjusted so that we can have an accurate result. So in the next chapter, we talk about these you, with concrete examples. The first example is not very interesting. It's just XOR example. The second one is kind of interesting. It's binary classification and the data set is in moon shape. Why is that important? So when you look at the data distribution like this, you realize you can't just use some naive algorithm like KNN, right? The nearest neighbors will not give you a desired result. Uh, so you have to build like a dense neural nets to do that. And since we're doing, in this case, a binary classification, right? It's not a regression. Uh, the loss function here, really, we use the binary cross entropy. If you go back to the previous one, right? So it's really just a recipe for you to pick the correct loss function and also the activation functions, right? So, so coming back to the binary classification example, we can see that for the loss function, we use binary cross entropy loss, and for the activation function, we use sigmoid, which also is correct according to this recipe, right? It's very good. Uh, but this is for the final. This is only for the final activation. Sorry, for the final hidden layer. For the middle hidden layers, most common ones are ReLU or leaky ReLU, right? So as you can see in here, the middle hidden layers, they all use ReLU, and the final layer, the shape is 16 to 1, meaning that this is the output, right? So we aggregate all the result and produce an output. And since this is a binary classification, we use sigmoid. So everything just works according to the recipe. And indeed it works, right? The classification is correct. So this is the power of neural nets or deep learning. Right? If you just use simple KNN, you won't be able to deal with this. You might be able to deal with a distribution of this with like dbScan or something, but not with naive KNN. So the next example is multi-class classification. The data set, the distribution is spiral. So it's kind of similar to the moon data set, only that this is not binary. Like there's more than two classes, so it's multi-class. Now, if we go back to the recipe, um, then we know for the activation function, we should be using softmax, and for the loss function, we should be using categorical cross entropy. And let's go and check. So indeed, for the loss function, we use categorical cross entropy loss, and the last layer, we have the softmax as the final activation function. And since we are outputting three classes, so there's three different labels, the last layer, the shape of the last layer is defined as this, right? We have three different kind of output. So yeah, everything just plug and play, check the recipe, plug and play. Very easy, very simple. Now it will be interesting to try different shapes of the metal hidden layers, like if we instead of using 64, we use 32, well, how does that affect the performance and accuracy of the neural nets? Those are fun experiments that we could explore, right? So the last one is the real world example. We use the minced challenge, which is the minced data set for handwritten digits. We should be able to the end goal is to predict handwritten digits. So there are 10 classes, right? There are 10 different labels. It's still just plug and play, same recipe. This is multi-class classification. So categorical cross entropy loss is the loss function and softmax as the final activation function. Yeah. And that's it. That's all for the walkthrough. Thanks for watching.